Steel deck does not fit properly over bolted moment connections. You know, you get this giant moment connection that's all bolted, beam to column, you got nuts or bolts sticking up, and now you go to lay the deck down and it's sticking up an inch or so. And that means you can't get all the concrete that's required on top of it. People get excited about fire ratings, etc. So a solution quite often is to cut the deck away and provide some other deck support. To prevent that from happening, do that ahead of time and make sure the connection is such that the deck can bear and change that detail. It's really a detailing issue. It's not something that you and I created wrong, but it's usually a detailing issue. This is kind of a dumb one, I think, but it comes up. Can open holes be left in members? And a lot of people think you have to have a bolt in the hole. We all know, like in the metal building industry, they furnish a lot of materials, a lot of extra holes for adjustments. The answer is yes, you can have open holes so long as you've designed a member for the holes, okay, then it's fine. The one little thing we find, again, I haven't found any firm research on it, but since I do a lot of crane buildings and get into fatigue situations, we have found that you get a better fatigue life if you do put a bolt in a hole and you torque it up. It sets up a little field of residual compression stresses around the bolt hole, so when it's pulled, you don't have quite the same stress level and fatigue. But that's an unusual situation. We do refer you here to the new 2005 specification, section F13, which deals with holes and beams, and those requirements have been lessened in the 2005 spec. They're more liberal than what occurred previously. So that's a very nice thing. Also a little ad for AISC. They have the lecture series now on the 2005 spec. I don't recall if it's come to Chicago yet. I assume it has, because you are the biggest city in the United States, so it should have been here. But if you didn't go to it, make sure you get to it, okay? Or you might hold off for a couple of years and they'll give you a reduced fee to come back here and watch it. So. But refer to the spec. Can mill reports be used to justify a larger load capacity? In my younger days, I know I did it. The rule of thumb today is, in general, no. You should not use a mill report. But a mill report can give you a good idea of whether or not the steel that you have has a higher yield strength than what you anticipate. Okay? A36 steel generally came in at 42, 43, 44 KSI. Okay? Quite an increase. A992 doesn't have the same percentage increases. But if you need some extra load and you have the mill reports and you see, oh gee, that stuff was probably 44 KSI, it might tell you then to do some extra testing, take some coupons, see if you really do have higher strength, and away you go. Okay. Now remember when, well, some of you remember, some of the people my age don't remember, when you were in school, the professor said steel is homogeneous and isotropic, and now we can look back at him or her and say baloney. It is not homogeneous and isotropic. It turns out prior to having A992 steel, mill reports, mill samples were taken from the webs of the section. Why did the mills do that? Because the webs are stronger than the flanges. Duh. Okay? They're rolled more. They can have a 10% greater yield than the flange. A992, the STM spec says you shall take the mill report out of the flange material. So we've solved that little problem. But if you have an old structure, that mill report came out of the web. And if you need strength in your flange, that's why you probably shouldn't be using it. If you need to take a sample, I've done this many, many times. If for chemicals, you can drill, take some specimens out by drilling, send them to the lab, then tell you what kind of steel you got. Usually you're doing that to see if you can weld to it. If you need some coupons, you can find a place where you don't have to repair it after you've taken a coupon, such as a joint where you might have a beam and you can take a piece of the flange out. And since that's a pin connection, it doesn't matter anyway. Some connection fit-up problems. Maybe here's something to learn. There's a lot of problems with fit-up of moment connections to weak axis of columns. Now I know you all have to work for architects and they don't want any bracing and all that nonsense. But if you can avoid ever making a weak axis moment connection, I encourage you to do it. They're problems. They're always a problem. Do something else. Either plead for some bracing or turn some columns, rotate some columns so that you can have moment connections going into the strong axis. There's so many things that can go wrong with that type of connection. Here's some continuity. Here's the web of a column. Here's some continuity plates, and we're going to weld a beam in there. I can almost guarantee those aren't going to line up. And for you young engineers here that have never read ASTM A6, I encourage you to go look at ASTM A6, which talks about the tolerances that the mill can give the fabricator in a beam. You know what, folks? The webs are not in the middle of the flanges. The flanges are tilted. The depth is not what's in the manual. There are tolerances on all that. And that can cause you big headaches. If you get some of those tolerances accumulating tilt, depth, with a connection of this type, you're never going to get to make that weld. Just isn't going to happen. I encourage people to, if they're going to have to do this, use some, really grossly oversized continuity plates. So now you got a good chance of this hitting with a backup bar, and you can make the full penetration weld you might need. But again, try to avoid it. I said use a big continuity plate. We're using A992 steel today. It's 50 yield. Remember that connection I showed you? Let's see here. You're transferring the moment, the forces from here to the continuity plate over somewhere, okay? Guess what? That has to be 50 yield material. Or it's like an A36 thing, so don't forget that. This was a friend of mine. He had a project like that where they found out that the continuity plates, these were 36 material, this was A992, so the moment connections were not good enough anywhere, and so what they had to do in the field was come into all the columns and weld new continuity plates on, put a little stub on the beams, and figure out how to get that moment in there. That was his solution. So it's a mess. Another problem that comes up is the bolted flange plate connections. This picture actually AISC Solution Center sent me when I was pleading for pictures. Some of you use this type of connection. I've used it. You've got some flange plates that are full pen welded, and then you have a beam that slips in here and you put the bolts in. What can I say? Tolerances. Provide plenty of shim for this type of connection. The beams may overrun. The fabricator may not get these in exactly the right position. The position may change due to the weld shrinkage. Okay? I did a project about 4 years ago where we had a big, heavy mezzanine. It was designed for 3,000 pounds per square foot. And we had a bunch of these connections because the beams were so massive we didn't want all that field welding. Okay? Unfortunately, the owner had the columns fabricated by one fabricator and the beams by another. So there was no way in the shop where they could sort of, hey, does this sucker fit? You know, and we had left plenty of room for shims, but they didn't fit. And thank God that guy's name wasn't Vince, because he thought it was our problem. We had to take all the top plates, air arc, all those full penetration welds out, set the beams in there, and then reposition the top plate. It was very, very expensive. Usually you can jack things into place or move them around, but it was very expensive. So you can jack them into place quite often, get the bolts snugged up, the bolts can pull them in place, but use shims. We use at least 3/8 inch shim stack on the bottom to make sure we got room. And you may have to remove the top plate, as we did in the project that I was mentioning. Look at the A6 tolerances. Fabricators may think about the weld detail and the weld sequence to keep those things straight, and you may have to heat straighten after you've fabricated. Some more on steel connections, beams too long or too short at a concrete wall. These solutions are fairly simple. You know, cut the beam, re-weld the connections if it's too long. You might use larger angles on the concrete to stick out to catch the beam. Field measure, replace the beam. I think the key here is to recognize concrete tolerances and to provide adjustable connections. Concrete boys are a little smarter than us. They have some really big tolerances. As far as vertical alignment, this is out of ACI 117. As far as vertical alignment, for heights 100 feet or less, 1 inch. Okay? For heights greater than 1,000 feet, 1/1000th times the height, but not more than 6 inches can it be out. Give me a break. Lateral alignment, 1 inch. This way on the concrete. Now, I will say, so some really neat things going on, and this was spearheaded by AISC. They've set up a committee now to get the concrete folks talking to the steel folks and try to get our tolerances in sync so we can work together. Now, generally, when they build concrete buildings, they don't do that badly. Otherwise, we'd have lots of field problems. But those are, if there's a dispute, those are all that has to be lived with. Here's just a few slides. Beam to concrete connection, welded, bolted. Usually have a weld plate, some studs on it here. In case I forget to mention it, the rule of thumb on size of weld plates going into concrete, do you know what it is? They can't be too big. If that's your wall, make it about the size of the wall, and they'll probably hit it okay then. So be generous, because it's not going to necessarily be in the right spot. It's as bad as anchor rods. Okay? If they don't get it in the form right, it isn't going to be right. So this one was a field weld solution. You can study this. A plate was put on one side and field welded into place. Same thing here. This was a welded connection. I won't bore you with studying this to death, because you can look at it and see. But of course, when you designed it, you had slotted holes this way because of the concrete tolerances. But even that wasn't enough, so you may have to do some things that are shown like in these slides. This is a single plate connection. fixed again at a concrete wall. Said existing plate was misaligned holes. What you want to be careful of in all these solutions, regardless of what they are, is you've got a rigid body, the piece of concrete. You probably have designed the beam coming in here as a pinned connection. So you don't want to create a fix where you might create so much fixity that now it's a fixed-ended beam. Now, nothing's going to happen to our wonderful steel, but you know, the concrete, the studs may break, the studs may pull out because they weren't designed for a big moment going in there. I probably shouldn't do this, and I have to restrain myself in these lectures when they're taped. But I had a superintendent tell me a few years ago, there's two things, Jim, he said, that you can count on concrete. And I said, what's that? He said, it's going to get hard and it's going to crack. And that's true. So when you're even designing concrete, remember, it's going to get hard and it's going to crack. And in that design, controlling cracks is the main issue, especially floor slabs, which we should talk about for half a day sometime. Embed's too small. You can weld on an additional plate. You might have an epoxy bolt on an additional plate. Prevention of this problem, oversize the embeds. Check your stud spacing. Provide nail holes. The fabricator should do this. Provide nail holes in the embeds so they assist in their installation. One thing that came up that neither Larry and I think, had thought about when we wrote this, I put down epoxy bolt in a new plate. Remember that, and this is true for the anchor rods too, when you use an epoxy, it gets more than 200 degrees. It melts. So be very careful in using a field fix with epoxy bolts in an area where you have a fire requirement. So you may have to add some fire protection or do something so that in the case of a fire, this bolt just doesn't poof out of the hole. That was a technical term, by the way. So be careful of that. Quite often the question comes up, can welding to embeds damage the concrete? And too much heat causing spalling of the concrete. I don't know of many cases where it's been an issue, but I think that it behooves you to use fairly small fillet welds, not great big full penetration welds. Look at the weld sequence. Provide a thick enough embed so the heat sink's big enough so it takes the heat away from the concrete. And we use 1/2 inch for deck bearing plates and 3/4 inch embeds for beam bearing kinds of things, just so you have enough heat sink that you don't over stress, I guess you would say, the concrete. Something that just came to mind is, and again, it's not in this lecture, but maybe you pick it up. After a fire, you know how to check whether the concrete's okay. They hit it with a fire hose, and if it doesn't spall off, it's okay. And that's true. And what about steel? Do you know how to check steel after a fire? If the steel is not deformed, it's okay. It has not been damaged. If it's been damaged, it means that it's bent, it's locally buckled, something's happened. But if it hasn't deformed, it's okay. Now, those are two rules of thumb that the experts don't tell anybody because they want to get nice fees to go in and say it's okay or it's not okay. But it's very simple. Interferences. This is a job we looked at after designing a condo. And this was supposed to be a continuous beam. And look, we got a little jog here came along, and we got some nice openings for interferences. It happens. This job was in an old steel mill. There had been a pipe in here. That's a 24-inch deep column. That's a little bigger than the recommended hole size. That building did fall down, and it fell down about 2 bays down, and it was due to this. The flanges just buckled under the weight of a snow load. But there was obviously an interference problem. In that same one that had the pipe, this is a classic. Well, that pipe's going to be in the way, so we'll torch out the beam. And now we put a really nice connection in there. Thank God it's in a positive moment region instead of a negative moment region. There's some quality looking stuff up there. That would have passed my test. Bracing interference. This was a job I did in Knoxville, Tennessee. Cold form girt. My dimensions weren't too good. I had the bracing interfering with the girt. I think I don't remember if I knew it or not, but the common way to handle that is to blow a hole in the web of the girt and thread the rod up through. No harm done. This Yahoo makes it really easy and cuts the flanges out of the girts, and right in the middle of the girt. And I wouldn't have known that the building had a liner panel on it, but this was the one area they hadn't put the liner panel up. So then I made them take them down everywhere, and by God, it was everywhere there was bracing. Just cover it up. Folks, it pays to go to the job site. I know some of you, you don't have fees to do it, but try to negotiate a fee to go to the job site. If you can't, I say go anyway. I think in the, perhaps I hate to admit it, the 40 years of practice, I have never gone to a job site where I didn't find something wrong. Never. Maybe minor, maybe major, but there's always something wrong. So think about getting there. You know what to look for. You can do it in a half an hour. Bracing interference, move bracing, cut out the interference, and reinforce as required. We reinforce the one I showed. Proper design and detailing to avoid interference and provide the compatibility in those details. Reinforcing, we could talk a lot about reinforcing members. You look at the shear and moment diagrams, if we still remember how to do that. I think we're more inclined to think what the computer's doing today. Check field, tolerances, select reinforcing elements based on strength and constructability. Remember what I said earlier, materials cheap, labor's expensive, and size what you need. These are just a few pictures of reinforced members. You've all done this. I know you have. I've done it. And the nice thing about seeing some pictures that somebody else did is saying, oh my God, I wasn't so stupid in doing that. Even Fisher did that, So just things like, plates on the outside of a beam, bent plates in here with some new plates like this, adding a member underneath. These are all legitimate things that one can do so long as you analyze your structure properly. Then you can do anything you want. But you got to analyze the structure properly. Some other ideas, the new plates, boxing it in, channels. This probably had to be done. Well, usually the problem is if you got deck or something up here, it limits what you can do on the top flange. You may have to do something like this. So each situation may be different, but these all work. Some general ideas on connections. Remove and replace the connection with a stronger connection material. Maybe there were rivets there. Put in some A325 bolts. You might be able to fix a connection by using X bolts rather than N bolts. You might add weld. I mentioned remove rivets. You might ream holes and use bigger bolts. You might add framing angles or a seat. You can do all these things. It's your brain power that controls it. Add welding. And there, I'll let you look for it. But in the 2005 spec, there's some new requirements on strength with bolted and welded connections together. That'll be a test for this lecture, to go back and look in the 2005 spec to see what you can do as far as combining weld strength and bolt strength. Extend the length of framing angles, add second angles. Here are just, again, some quick pictures showing where here was a seat, now we added a framing angle. Here was a framing angle, we extended it. Maybe add stiffeners. Again, it's just your imagination, whatever you want to do. This was field welding to get extra strength. Adding a seat to get extra strength. Adding another angle on the other side to get extra strength. So on and so forth. So we've got about 5 minutes before the break. I'd be happy to entertain any questions you might have, if you don't have any, or if you want to. If you're the shy and reserved kind of person, you'd like to come up and just ask them privately, that's fine too. So anybody, we have microphones so everybody can hear your really high quality questions, so don't worry about that. You know, everybody worries about asking a stupid question. There are no stupid questions. Anybody? Yes, sir. Do you want to use the mic? I think they want to record your wonderful question. Now make it easy so we can both look good. Okay. I'll try repeating it too. I do not, can everybody hear the question? Okay. I don't think there is any first hand or right off the bat kind of solutions. They do say you can use less than 4 in a fix, where you would say you have to guide the column during the fix. Okay, or guide the column until the other structure has been added to it. Okay. I would suspect that you could, though. I mean, it makes sense that you should be able to guide a column and use 2. But I don't think it's in the OSHA regulation. Larry, do you know it all?
Just like you said, you can use special erection procedures.
Yeah, but it's usually for the fix, special erection procedures. But good question. You know, the only exception, is what is real light posts, and I can't remember the weight. They're like 300 pounds or something. You don't need the 4 anchor rods, but that's an unusual thing. 4 is good anyway. You know, it really is a good requirement. It does stabilize that column better. Other questions? Yes, sir.
Over the last couple of years, we've come across a couple of projects where the materials between the column strength and the base plate have been shown up in the field to be different materials. And in some cases, the welding is not very compatible. What's the best way to track that down? You get mill reports, but you have to follow and making sure you know exactly what the mill reports are for and how you can really keep control of that.
Okay, the question is different material for base plate and columns and some welding issues primarily. Well, of course, there's nothing wrong with having a different material for the base plate than the column. And it's more likely that the base plate's going to be A36 material and the column's going to be 50 yield. That's going to be the common thing today. Okay? So as far as weld compatibility, there shouldn't be a problem with 50 and 36. Now, also remember, the thing I see so often is the weld of the column to the base plate is generally a weld that the requirements on it are nothing. They're just holding the column in place. until you get a situation where you might have moment or something in the base plate or in the column. Then it becomes important. But other than that, it's just holding it there. So to me, it's not a big... During erection, you've designed it for the structure being complete. Now, yes, it's good to get some decent weld there, okay? I can tell you that in my experiences with collapsed structures, if the weld breaks between the column and the base plate, which it will, if the anchor rods hold, it'll break. When that breaks, Mr. Fabricator will get held, won't get held, but he'll be blamed for bad welding. And the engineer may get blamed. But remember, we're designing that for the completed structure. We're not designing it for anything other than that. So if you look at the recommended amount of weld, it's not very much. One side of the web, one side of each flange. It doesn't wrap around. There's no need to wrap it around. So I don't think there should be a problem if the welding was done according to AWS. Because the common thing will be A36 base plates, 50 yield steel for columns. Other question? Okay. Oh, I'm sorry. Yes, sir. Is it okay to use a hooked anchor rod? It's always okay to use it. The point that I was trying to make earlier is it's probably safer for base plates to use the threaded nut because it has a superior pull-out strength. So even though I'm standing up here and saying, and my insurance company is saying, you don't do means and methods, okay? It's nice for us engineers to think about the poor slob in the field, okay? And we can do some nice things for him or her, but we don't tell him we're doing it for him, okay? So, yeah, it's okay. It just, remember, it does not have the same pull-out strength as the nut on the end of a rod. One more. Yes, sir.
Address the bolt and flange connection. If you have a deflection, moment connection, full penetration weld, and you have localized heating to straighten the plate, are you going to require ultrasonic testing after it? Because ordinarily that is fabricated in the shop and tested in the shop.
Boy, that had a lot of question in it because we were talking about this bolted welded in the beginning. I'm not sure I fully understand the question.
You said the bolted flange.
Bolted flange plate. Okay, they're sticking out there.
Right.
All right.
Top, bottom.
Right.
Top, bottom plate.
Okay.
Full pins to the column.
Yes.
If the heat is localized at the weld location.
Yeah, to move it. Okay.
Yes.
Would I require it to be
Follow-up ultrasonic
sonic testing? It would depend on the severity of things, I think, and the size. I don't think you would necessarily have to, no. But if it's a very critical structure, then, yeah, I would say do some limited testing to make sure everything's okay. That's a hard joint to check anyway once it's been welded. Well, you have to get behind. You know the problems with ultrasonic testing. You might create. I always shudder when the weld inspector is going out to the field because they're going to find stuff. It's their job, and so often it's not worth worrying about, but it just causes a lot of problems. Okay, let's take Steve, a 10-minute break.